I've given up on it. It's impossible to do testing in a test environment, any meaningful testing anyways, right? So, so you just like launch it into production and do the testing there. It's the perfect place to test. Seriously. Everyone thinks I'm joking when I say that, but that's basically the way we've been working for the last couple of years. And really the nice transformation that allows us to do this is actually moving to microservices-based architectures. If you actually have a properly architected microservices based thing, forget the microservices, crappy name, but for the rest of it, you can actually move to a regime where you can do all of your testing in your production environment. And when you can do all of your testing in your production environment, life becomes a whole lot better, because what you can actually do now is start running experiments after experiments after experiments after experiments and turn them around really, really, really quickly. And the key to getting good performance in any system reliably is one of them is to be able to do experiments very, very quickly. Because sometimes what you see in these systems is that the behavior is emergent, and which means it's unpredictable right from the get-go. And the only way you're going to see what's happening is to actually, have it meet the real world. And in that case, it's like, you can run an experiment, and you can actually get a really terrible failure by running the experiment, right? But in a large cluster in a microservices environment, it shouldn't matter if one thing fails. If one part fails, who cares? You have like 1,000 other parts that are there to pick up the bits, right? And so in terms of ease of testing, it's really been a game changer. And it's really funny because the first microservices-like architecture I was involved with, we wrote it in, if I say the date, everyone's going to leave the room right now because they're going to say, what can you possibly know about new stuff? And, okay, so the day, 1993, we didn't even have Corba. We looked at Corba and said, this technology is crap, we don't want it. So we wrote our own container, our own messaging backplane, and all of the other infrastructure that we need in order to create like a truly distributed microservices architecture with a DSL, by the way, for job control. And the DSL was actually used by semi-technical end users that were defining workflows through the system. And the key of testing in that environment was we could just deploy it to production and test it outside of the normal functional testing, and then we could see what happened in that environment. And then all of a sudden you get out into the real world and you try to explain this to people, and of course everyone's looking at you like saying like, you're from Mars. We can't write systems that way. They have to be stovepiped. And then, here we come forward, I don't know how many years later, and finally people are looking at it going like, oh, well, this is a great way of architecting systems. And there's now a whole bunch of tool support that I wish we had. We actually, we have containers. Well, we just had a nice conversation on virtualization about some of the pitfalls of performance under virtualized environments. I would say that this is completely off topic, but if you're interested, I'll continue for another minute or two. There are a lot of performance pitfalls to running in virtualized environments, right? One of the expressions I've had is like, you can't virtualize yourself into more hardware. So we just had some guy basically try to run the equivalent of 200 threads per virtual machine on a 64-way box, and I think there was, it worked out to be 200 threads per core across all of the things that they had installed there, and they were wondering about why they're having these GC pauses that were exceptionally long, and I was like going like, okay, you realize you're dedicating like about, less than 4% of your total CPU capacity, assuming you can get to it all, right? To each individual thread that could be potentially running on your system that's going to be demanding 100% of a core. So I mean, you can just do the simple math in that case and realize that, okay, you have a problem in this case, just in infrastructure setup. So there's some problems, but all in all, I think that we're in a much better place today than we were in terms of being able to design and develop these types of systems and actually have success and be able to do experiments in production and get rid of all the crappy testing systems that we have. I mean, I'll talk about some of the things here, but I can just say, one of the things we're going to talk about today is, this whole layer in this model that we use for helping us understand where our performance bottlenecks are. And there's one layer in the model that I put in there, and we gloss over it, and everyone goes like, "Ooh, that looks cool," and I wonder if like that. But it's absolutely, I would say, in a test environment, 100%. Well, you'll get it wrong 100% of the time, and if you get that wrong, everything else is wrong. So you're going to be wrong almost 100% of the time in any of your test environments. You might be close enough to the truth that you'll make the changes you need to make accidentally. But that's typically what we find. So people make the changes accidentally. So, okay, well, let's get into the real slides and out of the rant mode. Stuff that I was supposed to say, I think. You can read that. Oh, disclaimer. Oracle has their disclaimer. And because they have their disclaimer, everybody has their disclaimer. Mine is a performance tuning disclaimer. So that's pretty much it. In other words, performance optimizations are responses to highly localized events. And what works for you might not work for the other guy just because, well, I mean, even if you understand the idea of emergent behavior, it means that, even different systems running under slightly different conditions, well, the same system running under slightly different conditions are going to give you different results. So that's a challenge. Anyways, so typical customer application isn't performing to the sponsor's expectations, and users are waiting typically minutes or sometimes longer for the application to respond. And then you get into all of these wonderful situations. Here's a fun one, actually. Has anyone ever heard of the Apps for Apes program? So these guys in the Netherlands built a dating app for orangutans and bonobos. And okay, so what does this have to do with performance? Well, the orangutans completely destroyed the equipment because the app took too long to start up. Okay, so I hope your users aren't like that, but that's what happened. It's quite amazing. Anyways, it's a nice program. If you have old iPads and things you don't want to use anymore, you can donate, and they will let the apes make use of them after they've hardened them a bit. Okay. Yeah. So so what happens now? Well, of course, the developers get involved, right? Of course. And they start looking at the code because we're developers. What do? We look at code, and as we look at the code, we figure out. Okay, there's crappy code. What application doesn't have crappy code in it? I mean, I'll admit it. My applications have, a small percentage of crappy code in it. Be quiet. And so you get all of these weird solutions to problems, and sometimes you get into engagements and you have to spend hours talking to the management saying no, waste of time, don't go in that direction. This is we need to be going, doing something else, right? Anyways, and if you don't win, then you get into this particular situation here, right? People start changing code, and it's where's the problem? And then, the managers start getting involved, and of course, what do? You form a tiger team. Who here has been on a tiger team? Yes. So you all know how this works, right? Well, of course, who here in Sweden has been on it? Who's Swedish and been on a tiger team in Sweden? Okay, who's not been on a tiger team in another country? Because I always think of Sweden as being a much more friendly, cooperative country for some reason, and things tend to work differently. Or maybe the tiger teams work well in Sweden, but it's what is it? A team of specialists in particular fields brought together to work on a specific task. That's the official definition. The real definition is a forum where experts from different disciplines come together, express opinions that defend their specialities. That's, so it doesn't really work, right? And so everybody comes to the table with their own opinion based on whatever measurements they can come up with. Here's one that we use quite often that I pulled out of an engagement. And it was actually quite instrumental because when you actually do a breakdown and analysis of this thing in the context of the engagement, we're able to just basically come to the table with something that said, hey, now everybody has to pull in the same direction. Actually, this is just a definitive piece of data that tells you what the problem is when you apply it to a particular context. And what I find is when we're performance tuning, we know a lot of stuff. I imagine everyone here has been through university IT programs. Anyone hasn't? Okay. So I'll take it either you're too lazy to raise your hand or embarrassed to raise your hand or whatever. But the next question I'm going to ask is who here has actually been taught how to diagnose a performance problem in any of your university curriculum? So you're either too lazy to raise your hand or arms are broken or something like that. And this is a real problem because what we found in teaching developers how to do performance tuning is that performance tuning is fundamentally a different skill than developing code. So, and the strange thing is it's all based on the same knowledge, the same base of knowledge. So all of the stuff that I'm going to tell you about things, you already know it. I'm just going to repackage it for you to make it useful for this particular task, which I call a diagnostic a task, as opposed to what you're used to doing is being creative and creating code and solving problems that way, right? So you need the creativity to solve the performance problem, but you need the diagnostic skills in order to understand what the real problem is that you need to solve. And that's where we all fall down, is in the diagnostic skills. As a matter of fact, after you do diagnostics for a while, you recognize that other disciplines or specialties where you think that they should have good diagnostic skills actually all suffer from the same problems. In other words, try looking at how your doctor does diagnostic skills. You'll walk away maybe kind of a little concerned or scared afterwards. Some of them are good or not. So how do we get to a more structured approach to performance tuning? How do we bring rigor to the process so that we can make this to be a more predictable exercise? Something that we can say it's going to take so this amount of time to actually reach an end result. And one of the things that we see in other engineering fields is that when they have problems and they need to do tests, what they do is they introduce this thing called a system model. They model the problem. Okay? And that helps them bring structure to the problem. It helps them define the tools that they need to take the measurements they need out of the systems to help them make decisions. It helps them define a methodology or a way of tackling the problem. So really, what I want to do here is I want to try to introduce what I call jPDM, our performance diagnostic model, right? Which is just a very simple system model that models the system that helps us organize our thoughts and our thinking about what's going on in our system. Okay? So we need some elements in their model. So let's start building up the model, right? So the first question is, where do developers live? Right? Well, they actually live here. They live in the code. That's where you guys are every day. You're writing code. You're looking at code, solving problems in code. At least, that's what we hopefully mostly do, unless you're in an organization that spends a lot of time in meetings or something. Okay. Our code runs in this virtualized environment. So that's our software environment that we actually work in, right? So we have developers developing this bit, we have developers developing that bit, and really what we have here is something that's very, 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 very abstract. Software is abstract. We can do anything we want in software, right? We can have ponies that poo rainbows in software. So What happens next is it meets the hardware. And now we have abstraction meet reality. And when abstraction meets reality, we have to deal with the reality of hardware. It has finite capacities, right? It has finite volumes, finite throughputs. And quite often, well, in all cases, we have to understand what the granularities are, or what the chunk sizes are of things that we work with, because that will help with things like utilization. Like we have cache line at a low level. At disk level, we have sector size. At network, we have MTUs, right, for TCP. So we have all of these granularity things that we have to be aware of also when we're thinking about what's going on. CPU, number of cores, right? Well, on one occasion in our model, it was important to know how many divide units we actually had in the CPU. Okay? Because only on recent cores do you actually get 3 divide units on the CPU. Before that, you only got 1. So if you had all 8 cores doing a divide, they could potentially get all stacked up on trying to get through the divide. And the divide itself is, it's an expensive, it's about 40 instructions to clear an operation through a divide unit. It's probably one of the most, it is the most expensive instruction that you can run into. And you have other things like throughputs that are going to be controlled by clock speeds, right? So you have throughput on CPU, throughput on buses, throughput on memory, throughput on network, all controlled by clocks. And of course, there's other things that that are going to be controlled by clocks in here. Memory, again, capacity, throughputs. The allocators in Java have become so efficient in recent years that we can actually put so much pressure on the write-back channels that our applications can run slowly simply due to allocation rates within our application, right? It's not every way that we allocate is equal. I mean, so allocating a meg or allocating 100 bytes takes approximately about the same amount of time, right? But they're going to put different pressures on the bus. Chunk size, typically 8 cache lines are, if you look at even memory access, the memory access internally, if you look at like a controller and how it's structured and stuff like that, you're going to end up with 4 banks of memory. So when I strobe the line to get the data out of it, I'm going to have to strobe a bank. I can't strobe the bank till it's cold, which means I have to wait for all the capacitors to drain. Yeah, I know this gets down into physics and stuff like that. But essentially what it means is that I can only hit 1 bank every 4th clock, right? So what they do internally is they stride your sequential access so that it hits each bank just as it becomes cool. But of course, you can skip through memory in ways that are very predictable and very nice, and of course, you're always going to be hitting a hot bank. You always hit a hot bank. That's a 4x reduction in the performance of your application just simply because of how you're striding through memory. Right? Now, they try to do a whole bunch of tricks to try to get around that, but at the end of the day, that's the thing that you're facing. Yeah? We can talk about the same thing about disk. We have a certain capacity on disks, and there's a whole bunch of latencies that are in there. Even with SSDs, as fast as they are, there's still a bunch of latencies that we can talk about with SSDs. Network, our capacity is, we have 1 line per network card. It's a non-shareable resource, scarce resource. I mean, all of these slides come to you can sum them up and say that we do not live in infinite compute environments. And because we do not live in infinite compute environments, we need to have things that are going to help us negotiate how these resources get provisioned in our application. And that really, that's really the role of the operating system and device drivers and things like that, right? Queues and things like that. They're going to help us schedule who gets access to all of these bits of hardware. And I would say that there's a recent study by the University of British Columbia that looks at thread scheduling. And I can say that, from that paper, you realize that thread schedulers are less than wonderful. at it being efficient in scheduling things, and you can get into some strange harmonics on top of that. And if you add a hypervisor in there, you know, all bets are off. Right? So there's possibilities that you can't even saturate a core, just simply because of the conditions in the runtime. So that's where abstraction meets reality. We have an operating system with some hardware that's actually going to define our capacities and our throughputs, and it's going to define, you know, what our maximal performance is in our system. And so we have our abstractions running on top of that. You know, so when we look at this, we're going to say, okay, there's, whoops, sorry about the strange thing going on there, but if you look at all this, you can say, you know, really we have something that's missing. There's absolutely no dynamics in this particular system, right? So we don't know we have a problem because we have no pressure on the system. So we need something that's going to add pressure on the system. And so to add dynamics, we need to actually, oops, weird things. Sorry, I had my machine core dumping. I intended to take those things out, but kernel panicking, so it's been having fun doing stuff. So, you know, in terms of the dynamics, you can ask the question, are we going through this again? Yay. Remind me to take those things out. Oh, every time the screen flickers, I just think this machine is going to die. It was having a heat problem, so it just turns off like that. Okay, so the question is, you know, so here, you know, here's an example. Like, what's faster, bubble sort or quick sort? Sorry? You're not allowed to answer. Okay, so if no one heard that, so you know, who hands up for bubble sort?
It depends on the case.
We have one. Hands up for quick sort. For all those who didn't put their hands up, I'm going to ask again. Bubble sort? Quick sort? Don't know yet, neither. Or it depends. Right? So it's actually going to depend. I mean, we have this big O notation that gives us like worst case analysis. You can remember all that stuff, right? So I'm not going to bother with that. You know, here's the truth. Bubble sort just gets onto it. You know, just starts doing it, right? Whereas a quick sort saying, okay, I got to do all this stuff beforehand and set up for it, and you know, you see the same thing with parallelism, parallel streams, stuff like that. You get like set up and tear down activities afterwards, and you can see that the overhead of doing this means that up to a certain size list, the bubble sort's faster. But after that size, the quick sort takes over. Okay? So now the question is, when you're sitting in your cubicle coding an algorithm and it needs to be fast, what are you going to choose, a quick sort or a bubble sort? Sorry, yeah. What are you going to choose? You're going to choose the quick sort? Yeah, okay, of course, why not? Because you're hoping that, you know, the overhead costs are going to be basically swallowed up by the size of the list. So you're making a guess, right? And really what we want to do is try to prevent guessing when we're making these types of decisions. What we want to do is we want to add another layer into our abstraction, which basically says that basically says that you know, here's what the pressure looks like on the system. So now we can take some measurements based on what the pressure looks like, so that you know, we can make a sound decision rather than making a guess here. So really in this case what I want from our system model for doing the diagnostic work is to have something that's going to give us a hypothesis 3, very methodical, top-down method of tuning this, or arriving at a conclusion as to what the particular bottleneck is. So I'm going to add this basically actor layer. Sorry, I'm going to have these things all through here now. I'm going to have this actor layer based on the top, right? So what we're going to see is that actors are going to add the dynamics to the system here, right? And they're going to drive load onto the application. The application, again, is going to drive load onto the JVM. Then the JVM is going to drive load down onto the hardware and start consuming the hardware. And then what we're going to do is we're actually going to look at the pattern of hardware consumption. And once we have looked at the pattern of hardware consumption, what we're going to do with that is we're going to go into this investigation, which I call identifying the dominating consumer, the CPU. So when we have the dominating consumer, the CPU, what we're looking for is the activity that is dominating how the CPU is being consumed. Okay? And this is going to be taken as a ratio. Quite often what we're used to looking at in performance metrics are absolute values. And quite often what we find is that ratios give you a much stronger indication of what's going on, and they'll give you a much better indication as to what the scalability limits are on your application. So in order to find the dominating consumer, we're actually going to try to look at the CPU counters, and then we can look at it, and we're going to have some problem because the application and the JVM are intertwined. So in this case, what we do is we do some garbage collection analysis to determine if we have a problem that's running inside the JVM or if we have a problem that's actually that we can attribute to the application. Now, at the end of the day, the vast majority of the performance problems are going to be a result of how we've written our application. So the destination will be the application, right? What we're talking about is how do we get to know which part of the application is causing us the grief. So in terms of dominating consumers, we have application, what we call JVM. This is going to be a system dominance. And we have this other category down here, which unfortunately gets buried in the bottom here, which is none. Okay, so application will cover execution types problems. JVM will cover memory issues. The system is going to cover problems between how the application and the system is interacting. So am I driving the kernel too hard for the particular workload that I have? And if I have no dominating consumer, that means that I have no ability to actually saturate the CPU at all. Okay? And that will come with resource starvation, in particular thread starvation issues. Okay, in terms of analysis, I'm going to ask the question, is my system CPU time greater than 10% of the user time? If I'm in this particular condition here, then I'm going to say that the system is the dominating consumer dominating consumer and of the CPU, and it's the thing that's controlling how the CPU is being utilized. And the tools that I would actually use to figure out why we're in that condition, well, there's a list, a list of some of them. And there's plenty more tools that we could actually use depending on the type of problem that we're actually facing. Okay? So we want to somehow do some system profiling or some performance counters that are being kept by the kernel. We want these things to be exposed so that we can understand why the application is causing the kernel to work harder than it should. Now, if I can't drive the CPU to 100%, that's another issue. I should, in just about every case, be able to get the CPU running hot. Think of it this way, right? I have an application, it's not responding in the amount of time that I need it to respond in. How am I going to get it to respond faster? Well, I need to soak up the CPU. If I can't soak up the CPU, then I have to ask the question, why can't I get the job that needs to be done into the CPU? Okay? So that's the question, right? And that, like I said, that tends to be some sort of resource starvation situation. Maybe it's a thread starvation issue. It could be a thread starvation issue because the threads are basically bunged out on long-running system calls. I think maybe not a good story for this time, but I can tell you how I brought down Lufthansa's website basically by having a single-threaded process in the background do something for a long period of time and have the thread pool exhausted on the front end. Okay? Thread starvation. In this particular case, all the threads they were there, but they got sucked up doing something else, waiting for a resource that everyone was dependent upon. Yeah, I did that accidentally, by the way. And yes, I've told Lufthansa. And yeah, anyways, it was quite fun. So the question is, if we can't force good saturation on the CPU, then we have to look for this particular condition. And one of the most effective tools for doing that is just simply a thread dump, right? And with the thread dump, you can look and see. I can basically inventory all of the threads, and I can figure out, okay, what are they doing? Who owns them? Just to answer basic questions like that and understand. Now, the demo I was supposed to run today, Heinz gave it to me, and I'm not going to because my machine won't survive that one. The first thing I did was when we looked at it, I said, okay, it's running basically 100% CPU saturation. First thing I looked at it, and I said, okay. But it was running one core full out. So the first thing I did as an initial, get an idea of what's going on, was did a thread dump. And I inventoried the threads, and I found that there was one thread associated with FX that was running 100% of the time. Okay, now I confirmed that later with another tool while rebooting my machine constantly, but that was the first step in saying, okay, this is where we need to go. That's the path we need to follow in order to figure out, what's going on. Okay, so if we can get good saturation, then I'm into a different class of problems. Okay, so I'm going to ask, is it memory efficient? And that's where we're going to do the GC analysis. There's other ways you can determine memory efficiency, but I think this is the easiest. We'll just take a GC log and we'll do an analysis on it and determine memory efficiency. If we are memory efficient, then we have some algorithmic inefficiency. Okay? And so now I'm going to look at execution profiling, this particular application, to understand where the algorithmic inefficiency is. Right? So what we've tried to do here is come up with a taxonomy where we can categorize all the different type of performance problems that you can run into and say, okay, this is a step in to help you eliminate the ones you shouldn't be looking at, and these are the ones that you actually should be looking at. So for memory, sorry to say, whoops, we have two problems here. One of them is we have a technical issue with how the garbage collector is tuned. The other one is that we have a memory inefficient algorithm in our application. And what we actually need to do is find where the memory inefficiencies are by using a memory profiler, not an execution profiler, but a memory profiler. And that will tell us, okay, where the allocation hotspots are in our code, and we can go in and correct them. Okay? You can't tune an allocation hotspot out of your code, right, by configuring the garbage collector. Right? So, I've had people come to me and say, we want you to tune the garbage collector, and the first thing you do is you look at this and say, sorry, I can't do it. You have an allocation issue, right? And they typically don't accept that, and they'll find another consultant who will say, yeah, I'll tune your garbage collector for you. But, yeah. That's the way it is. Okay, so we look at the expression of CPU consumption here. You can see that this is passively dominant. So this is going to leave the CPU mostly idle. And no matter what you do to try to soak up that extra amount of CPU that's idle there, you're not going to be able to get to it. It's simply not available to you. Okay? You can add more threads to this system. If you do, the most common reaction is that your CPU utilization is going to go down, not up. Okay. This is going to be aggressively dominant. In other words, I liken this to, when your kids, when they're young and playing, it's like, the passively dominant is like, my toy, I'm not using it, and you can't either. As opposed to aggressively dominant, it's like, my toy, I'm using it, go away, right? If you run into that situation. And that's really, I think, the best way, the analogy you can use to describe the situation. In terms of measuring consumption, that's kernel time, that's idle, that's user time. That's why we need the GC logs to tease these two things apart. Okay? So, what's a tool we can use? Well, okay, the cheap one is just vmstat. VM stack gives us a bag of counters. You can look at your particular system unless you have a Mac or Windows. In other words, you'll have to use other tools in those cases. But you can, you're just going to get a bag of performance counters out of the system. Now, fundamentally, these counters are lying to you, but it's sort of a white lie, so you don't have to worry about it too much. It'll still work, but just recognize that these are lies. Okay? So we're going to focus on this column over here, which may have 4 or 5 or 3 columns, depending upon which version of VMstat you're running. This is probably one of my favorite ones, except for what's missing here is steal time, right? So if you're running in a virtualized environment, you're going to see how much frequency, CPU frequency was stolen from you by having other VMs take it away from you. In those cases, if you get significant amounts of steal time, then that's saying I'm overloaded, and I need to move some of the processes off to another machine. But essentially what we're looking at here is user time, system time, idle time, and wait time. Now, one of the lies that we have here is idle time. Not all idle is idle. And if you have wait time missing, you can be sure that wait time is included in the idle time, right? But wait time is something spinning in the core, meaning it's idle as it's not doing anything, but the core is not available. So you can't really think of the core as being available when you see idle time, right? But at least with the wait time broken out, we can get a better idea of what the real idle picture looks like. So in this case, you can just run down the two numbers and just do the maths. Now this 10%, I'm going to give you the 10% number that I gave using the flowchart. It's a fuzzy number. In other words, that's 10% we use because it's easy to remember. It's not the real number, and the real number varies. So we actually use machine learning for this type of analysis because the machine learning will adjust to the fuzziness when doing the analysis. But this is good enough. Okay? So I'm just going to ask the question. Take the user time, divide by 10, and ask, how often is system greater than that? Okay? And you can see in this case, we are system dominant. Because, 1.5, if we go down the middle, 1.5 is less than 43. So, as a matter of fact, since all of those numbers are over 10%, anything you can put in the user column is going to be a problem. So, in this case, you can ask the question, okay, you have other counters here you can look at, and maybe with the other counters you get an idea of what the underlying problem is. I think in this one here, it looks to me like given all of the wait time that we've accumulated and the block out activity that's indicated in this particular column here, my guess is that this is a disk I/O issue. And we see this quite common, and especially in systems where people haven't really thoroughly thought through how they're actually logging. Okay? I would say that logging is one of the common bottlenecks that we find in applications. It's about 60%. And the reason why we get to 60% is because, no one figures out how much logging costs them. But try it sometime. Turn off all your logging, run your application. You might be surprised. Okay? I would say not even just turn it off. It's like, make sure you somehow rip it out. Because anyways, that's another rant to go on. Okay. So that's basically our model here that we're going to use to help us define who the dominating consumer is of our system. What we're going to do next is we need some sort of process to benchmark this, right? So normally what I'd like to do now is say, give me a virtual machine out in your cluster, and we'll instrument it, and we'll take all the measurements off of there. If you actually have to go to one of these old style, performance testing environments, and there's still some places that really are forced to do that. In this case, we're going to follow this particular process, which is like figure out, get our environment set up, get it quiet, make sure that we understand what our performance requirements are, we have to build the actor layer. That's the part that's impossible to do, right? Because that means you have to actually, for this particular model to work, what we have here is a model that says, okay, since this is a model of my real system, then I actually have to have my real system there. And since the actors are part of the system, that means I actually have to have my real actors. Okay, well, we can't have the real actors in a test environment, so we set a simulation of the actors. And so the whole model, the whole simulation now is, is basically how close is our model actually to reality, because the farther it is away, the less likely it is we're going to get a good answer out of the whole thing. And if we mess up on the actor layer, which is like almost impossible to get correct, then you can see how this whole thing is going to quickly fall apart. Fortunately, the base metrics that we're looking at, in order to do the diagnostic work, we can get them out of a production environment almost for free. Since they're almost free, that means we can easily do the diagnostic in a production environment. And you add in a few other tricks, like if you don't use commercial profilers, but actually build your own, then you can build the profilers in such a way that they won't affect the performance of your system either, right? Profiling is a whole other topic that, has anyone covered profiling in their curriculum? Man, we go to some good educational institutions, right? Let's cover everything. Okay, that's cool. So I don't want to go on another diatribe against profiling, because that would take another hour at least. But we can build profilers that we can actually run in production systems. The trick is to not collect useless data. So if you look at what most profilers do, is they start, you look at any monitoring or profiling system that we use, how much of that data do you actually look at? You probably have like gigabytes or terabytes, or how much does Twitter have? There's someone, petabytes? I have no idea. How much do they actually look at? Yeah. Why are we collecting it? Well, we're collecting it because we don't know what to collect. So I just gave you the key performance indicators that you need to collect to help you understand what's going on in the system. We don't need the other stuff unless these things are bad. If they're bad, that's when we need the other stuff. Right? So don't bother collecting it. Or if you do collect it, don't bother storing it. Most of the data you need is about 15 minutes prior to the incident. You don't need anything else. So if you just put a ring buffer in an mmap file and just write the data into the ring buffer in the mmap file, that's going to be the cheapest, absolute cheapest way to log in when you get a failure. All the data that you need to do the diagnostics is going to be right there in one shot. Right? And you don't even have to turn it on until you see your system get into the condition where it's starting to express the problem. So you get really, really, really cheap, highly scalable profiling that way. You can actually really run in production environments. Okay, so anyway, so here's the process. I assume you can read Java code, so that's why I wrote it that way. It's better than words for the whole thing. So, so we're just going to find the first bottleneck, and we're just going to keep going through this particular process, finding one bottleneck at a time, knocking them out, because we're going after the primary bottleneck. I think we said yesterday to the G1 guys, I said, anything before the primary bottleneck is a waste of time. Anything after the primary bottleneck is an illusion, right? So we need to go right after the bottleneck. And so there's only one, the system, theory constraints says there's going to be one bottleneck that's going to be expressing itself at a time. So that's the one we want to go after. And we'll iteratively go through them this way, right? So that means we need all of this monitoring stuff. Observability is very important, and again, that's observability is another session unto itself we can talk about. And we need something to do the simulation, and there's a whole bunch of different anti-patterns that we get into that we can talk about when you're doing performance benchmarking. If you want to talk to some of them, Gil Tennant has some wonderful stuff on how to measure, and he talks about coordinated omission and those types of topics. So you can go there and look at that. Mine are just really simple. It's like, data light. How many times you see somebody do a performance test where they dump like a couple hundred records into a database? What happens to all that data? It gets cached. And now we're doing cache to cache, basically cache performance as opposed to real system testing. And we've seen some really interesting failures because of that, right? So we want to make sure that we have, data that has good volumes and good veracity, feeding the application and feeding the test harness. There's no point in having a terabyte of data feeding the application if you only look up like Mickey Mouse or Donald Duck. That's your test case and your test harness. In other words, you need to have a good amount of data there to basically apply the right type of pressure on the system. And what time are we supposed to go to? I don't know. Okay. Sorry? Oh, we have 5 minutes. Okay, good. That means I survived this whole thing. Time for a demo. Okay. So I had to resort to an old demo. I apologize for those of you who might have seen it before, but I know this one is not going to crash. I'm hoping this one will crash the machine. Let's see what's going on here. This is when I should have my glasses out. Yeah, I can do it here. So basically what I'm going to do is I'm just going to share the screen so that you can see what I'm doing. That might help, right? Mirror the displays, in other words. Okay, so we can see. And I'll make this bigger. You can see what's going on. What's that? Now you can see, yeah. I think my graphics card is shot, and there's some other heating issues here. So I'm going to bring up some monitoring. If we had more time, we could have fun actually having you go through the entire diagnostic process here, but I don't think we do. So what I'm just going to do is I'm just going to run this thing here. And so we have our application running. And we can look at it this way, and we can ask the question, right away, as we're running this particular little baby application. Right? Who is the dominating consumer of the CPU? I'll bring some numbers up here, because I think this thing is actually lying. No, it's not. It's good. Well, the dominating consumer actually is in user space, okay? We don't know if it's application or JVM, so we don't know if we have a memory issue or an allocation issue at this particular point in time. But what we would do next is I would open up the GC log and I would do an analysis on the GC log. Let's see what the temperature is. Yeah. Sorry about this. It's really bad. I'm not going to let it go to completion, if you don't mind. I'm just going to stop it right now. I think we have a GC log, hopefully. Yeah, we do. So what I'm going to do is I'm going to bring up our GC log analysis tooling here, which I know some of you are familiar with. And I'll make it smaller so I can make it bigger. And what I'm going to do is I'm going to go to, where are we, desktop, drink, and there's our GC log. I'm going to run it up into here. And I'll just do a really quick through the analysis here. So I think, we can look at the summary. We can see, okay, so we're running a parallel collector combination here, but somebody made some calls to system GC. Probably want to check that out to see if that's not a problem. We can look at the heap after GC. You can see the system GCs are clearly marked down here because they're marked down here outside of the range of the benchmark. That's probably set up crap, so we can ignore that. And we can look at this whole thing and say, yeah, we're using about 350 megabytes of memory, and everything seems reasonably okay. So we can go through some of the things here. And then we look at this particular chart, actually the pause time picture. It's like minimal. Look at summary, we're at 99%. So it doesn't look like the garbage collector is really an issue in this particular case. So we're now leaning towards, there's some algorithmic problems in the application until we actually get into like allocation rates down here. And you can see with the allocation rates, we're at about somewhere between 6 gigabytes per second, right? My magic number here is about 1 gig per second. So that's my red zone. Anything above 1 gig per second, I'm going to start saying, okay, probably we can get some really good efficiencies by looking for allocation hotspots and taking them out of the code. As an example, we had an application that was running at 1.8 gigs per second. We managed to get that down to 0, but the transactional rate went from 400,000 TPS to 25 million. So it was a nice improvement, shall we say. So in this case here, I think the application would go and run to completion in about 120 seconds. And when we deal with this particular allocation problem right now, which is attach a memory profiler, and when we attach a memory profiler, we'll look for the allocation hotspot, and I'll also have the allocation profiler try to tell me what the code path is into the allocation hotspot so that we can do an analysis and figure out. Unfortunately, we don't have enough time for that to finish that off, but really, in this case, once we get rid of that problem, this application benchmark will finish in about 7 seconds. So we'll knock off about 112 seconds off the runtime by by reducing the allocation hotspot out of this particular piece of code. Okay, so you know, and then if there's other things that need to be done, then you know we can again go through the same process again. So it's really like a wash, rinse, repeat type process for doing it. Let's go just back to slides. So if you look at it, we are in this particular issue here. We're at dominating consumer 2. I got rid of the first one previously. And really what we're saying is like, we're able to saturate the CPU. We looked at the garbage collection logs and said, are they memory efficient? The answer was no. We did do some memory profiling, in this case to find the allocation hotspot, use that to debug the application, make the code change, retest. You know, what about our customer who was this issue? You know, again, now we can ask, who's the dominating consumer of the CPU?
System.
Obviously system. So now we're looking for a completely different problem in this case. I'm looking for what is the application system interaction that's causing the grief. In this case, you know, we had a Hibernate ripple loading problem. So that was many small calls across the database that were handled very quickly by the application server, okay? Now, the network guys in this case said everything is okay. The database guys said everything is okay, right? It's only the application guys that were complaining. And so when you get everyone to the table with this type of analysis, all of a sudden you can realize that, okay, if it's not coming from that direction, if the service providers are providing good service, right, and the consumer is sitting on this side of the table, you know, then you have to ask, okay, how is the consumer interacting with the service in this case? Right, so I might have time for any questions, or you can just bugger off to lunch also, and I don't mind. I know everyone's hungry now. So do you have any questions? Yes, sir.
Yes, about logging.
About logging?
The 60%.
Most of it is due to what I call object creation of things that are just absolutely never, ever used.
But would you say that it's the application that is doing logging in the wrong way, or is it the popular frameworks that are forcing applications to do it
Yes.
the wrong way? Both?
Yes.
Okay.
I would say that I would like to see logging actually moved up to more of an architectural requirement-driven process rather than just having developers in their cubicle trying to say, oh, that seems like an interesting thing to log, right? Because really this is a problem of accumulation of things happening over time without any clear direction as to how to or what needs to be logged. And generally this is where you should have good conversation with your operational people. They should be setting requirements. Or if you're deploying a product, then you should be at least talking to the support people to help to have them understand what it is that they need in order to support this application when it actually starts running. The rest of it is, developers debugging stuff, mostly, right? And, and that's useful logging, but I think that, you need to take care of actually how much is there and how much is really needed. Yeah? Any other questions? I think there's somebody back there had a hand up for a second. Stunning. Thank you. Enjoy the conference.